recording. So it's a pleasure to have Patrick Draper here with us today. Has a very interesting title, The Sitter Decays to Infinity. So this is the second to last seminar in our series, so please take it away, Patrick.
All right, well, thanks very much for the invitation. This is, I think, the first time that I've given a talk at Minnesota, so to speak. So those of you that I haven't met, that's a pleasure. And I do appreciate everybody showing up this close to the end of the semester. I know we're all getting a little bit of Zoom fatigue. Most days I think about deleting it, but we soldier on. So thanks for being here. I'll try and be interesting. This is some work in collaboration with postdocs Isabel Garcia at KITP and Ben Lillard at Illinois. And I guess you're all familiar with the drill by now. Just shout to interrupt. I can't see the chat window, but please just ask questions. And this is work in progress. I was not so bold as to put a 2020 archive number here. We can hope, but so anyway, yeah, any questions welcome, and then they may help guide our thinking. Okay, how do I advance? Evidently I do that, okay. So this is the one quasi-phenomenological slide in the whole talk. We know from observations that to within some tolerances, the universe appears to be entering something like a de Sitter phase of expansion. And it has a very low vacuum energy density on particle physics scales, but there's some evidence now or constraints from cosmology that tell us that the equation of state, the parameter is of order -1 and relatively constant. So there are different ways that the universe could continue evolving from that point. We might be entering just a stable de Sitter phase, and that's it. We might be entering some kind of metastable de Sitter phase, like this case, where we're in some false vacuum that can tunnel out. Maybe the potential looks something like this, or maybe we're in a very slowly evolving phase like this, and we just haven't reached observational precision to see that evolution. And of course, the metastable phases and possibly even the slowly evolving phases can end by some tunneling processes. Keep hitting the wrong button, okay. So there are many known tunneling processes in cosmology. Partial list is the ordinary Coleman-de Luce process that I'll talk about for comparison throughout the talk, Hawking-Moss processes, decompactification processes, and the focus of today's talk will be bubbles of nothing. So I want to discuss what it means to have bubble of nothing tunneling processes coming out of metastable de Sitter vacua. So this is the outline. I'll start with Witten's bubble of nothing and give a brief overview of 3 physical pictures that sort of help understand intuitively what a bubble of nothing is. It has this kind of silly name, but what is it actually? It's not so mysterious. Then I'll talk about how to add a potential and what it means, why we need to add a potential, what it means to do that, and go over some relevant potentials of interest and criteria under which bubble of nothing type tunneling processes exist. And the ultimate goal is to do some amount of analytic and numerical analysis of these processes and compare the tunneling rates to ordinary CDL rates when they exist. So the original bubble of nothing is due to Witten. It describes the decay of just ordinary flat Kaluza-Klein space. So here's the ordinary flat Kaluza-Klein metric. It has a structure of R4 cross S1, and the S1 here will have a periodicity 2 pi r. And there are at least 3 ways to picture the bubble of nothing solutions that describe the decay of this space-time. And each one illuminates a different aspect of the tunneling event. So I'll go through each one of these briefly. The first is a gravitational instanton picture. The second is a barrier penetration picture. And the third is to formulate as a CDL problem. So the original description was this 5D. By the way, is the screen visible, or is this thing over here blocking it?
We can't see the Zoom window. If
you
that's
can't
what
see
you're...
Okay, all right.
No.
My student has had problems with that recently. I just remembered that. Okay, so
yeah, it looks clear.
It's fine. All right, thank you. Okay, so the first is a 5D picture, which is that Witten's bubble is nothing but the Euclidean continuation of the 5D Schwarzschild metric. So we start with the 5D Schwarzschild metric over here. We continue it to Euclidean time, And in this case, the coordinate, the radial coordinate, static radial coordinate r, ends at what we would have called the horizon, r. So unlike the Lorentzian picture where there's something inside the horizon, in the Euclidean picture, time is periodic and the geometry is smooth at the horizon if the geometry ends at the horizon. So you need a particular periodicity of time in order to avoid a conical singularity. But then the picture of the space-time here, I've suppressed a couple of 3 directions actually. The space-time looks like this. So we go from a vacuum, which is just a tube, the S1 direction on the cylinder going this way, and the gravitational instanton has that direction smoothly capping off at some location in the Euclidean spacetime.
Patrick, I'm
Yes.
sorry, but let's say that we're considering the limit where it becomes 4-dimensional. Let's say that the radius of this extra dimension goes to 0, right? What would be with the picture?
So there's that's happening at this point here. And asymptotically, I've assumed that it's fixed to some fixed finite size larger than the string scale or the Planck scale. So are you asking about the what happens locally, or?
No, because I'm wondering that in this way, if this extra 5th dimension, if this radius goes to 0, then it's not distinguishable from 4-dimension, right?
Correct.
I mean, then we do not see this Kaluza-Klein excitation, whatever, right?
Correct.
So in this way, we are back to it. And I'm wondering how, I mean, this geometrical limit where this radius of 5th dimension is small, how it reflects in the picture. Not just me, I do not have enough imagination to follow.
Right. Yeah, well, actually, that's sort of going to be the focus of this talk. So I will eventually dimensionally reduce. And if you don't see any KK excitations, if you can't see above the Kaluza-Klein scale, then this whole thing can be described from a 4-dimensional picture that looks very singular, but it's smooth in 5 dimensions. So that's kind of,
so in this way, there is a singularity in taking r equal to 0. So in this way, you are sensitive to 5th dimension indeed.
Yes. So this is a very 5th-dimensional process here. This closing off requires the 5-dimensional picture. We'll see how it looks from a 4-dimensional description, and it looks quite ugly, but it turns out that 4-dimensional description is also useful. So I'll spend some time on that. Yeah.
Okay, thank you.
Okay, thanks, Arkin. Okay, so the main takeaways here from this picture are that this hole in space-time, which I'll refer to as a bubble, and the size of that bubble as the wall or the core or the bubble size, those are related to the asymptotic size of the space-time. In Witten's bubble, the size of this hole that has appeared is the same as the asymptotic size of the Kaluza-Klein direction. The Euclidean action of this thing, so this is a gravitational instanton, and the interesting thing is its Euclidean action. Turns out that comes entirely from Gibbons-Hawking-York boundary term at infinity. The 5D Ricci scalar vanishes. This is a flat, empty solution. So the whole action comes from a GHY term at infinity, and this will play some role in the talk. So keep in mind that Witten's bubble has action pi squared r squared. The second interpretation of bubbles of nothing, and I'll just go over this very briefly, is to try and formulate it as an ordinary quantum mechanical tunneling problem with a single collective coordinate describing the size of a family of bubbles. So what you want to do is find a family of spatial configurations that behave like bubble states, and they'll be parameterized by some bubble size, which I've written here as RH. And you want to find a convenient family that interpolates from 0 bubble size, which is empty Kaluza-Klein space, to the nucleation point, or the bubble that nucleates for Witten's bubble. And it turns out that it's fairly easy to write down an analytic set of bubble configurations that do this, and you compute their Hamiltonian mass, and it follows this blue curve here. So this is a nice picture for understanding why Witten's bubble is actually just an ordinary barrier penetration problem. In this one-dimensional subdirection of field space, it really is tunneling out through this barrier. And this will not really play a... A
Can I ask
question?
a quick question? What is the physical interpretation of gamma in this context? Is it?
Yeah, gamma is going to set the asymptotic Kaluza-Klein circle size. So the periodicity for this family is given here.
I see. That's an input, so you don't want to vary it. That's why you're fixing.
Exactly. Yes. Yes. Thank you. I should have said that. So this is a one-parameter family that has constant asymptotic behavior equivalent to the original Kaluza-Klein space.
I see. Excellent.
Yeah. So this family for the Witten bubble, it's the easiest one is Euclidean Reisner-Nordstrom, where you don't have the gauge field, you just have the metric. So you have two parameters, Q and M, and if you fix gamma, that fixes one of them. And then you can take the other parameter to be the bubble radius. You can also do this for a more complicated set of bubbles of nothing that describe some tunnelings in sort of Kerr-like metrics, and those have a physical meaning as some decay of solutions with background magnetic flux. So there's a generalization of this, but this is the simplest one. Oops. Okay. All right, so the third interpretation, which is the one that I will use mostly today and touches on what Arkady was asking about, is to convert the bubble of nothing to an ordinary Coleman-DeLuccia problem using dimensional reduction. And this has been noted a number of times in the literature as a useful thing to do for various reasons, and we'll try and get more mileage out of it today. So there are two steps here. First is a dimensional reduction, and the second is writing as a CDL problem. The dimensional reduction part takes 5D gravity with a compact submanifold and turns it into 4D gravity with a massless scalar. And the sort of simplest way to do that is to just start with your 5-dimensional metric in a conveniently chosen parameterization where you have some dilaton or modulus phi, which is multiplying the 4D metric of interest and a different power of it multiplying the 5th dimension. And the sign choice is conventional. I've chosen the sign here of this exponent so that large values of phi correspond to the compactification limit. So at large phi, this becomes small, and that corresponds to a small radius locally for the 5th dimension. So you can take this metric ansatz and you plug it into your 5D Euclidean bulk action, the Ricci scalar in 5 dimensions here. And what you get out is 4D gravity minimally coupled to a potentialist scalar modulus that has a canonically normalized kinetic term, it's a 2 out here. And it's completely the same as far as the equations of motion are concerned to just starting with the scalar modulus. But there is this extra total derivative term, which can play some role in evaluating the bulk action when there are 4-dimensional singularities. So this term here doesn't affect the equations of motion, but it does contribute to the Euclidean action in some cases. So we can take this ansatz that allows us to reduce 5D.
For this term to play the role, I mean, total derivative, it should have some topology, right? Because otherwise it doesn't matter, right? So I'm wondering if there is some kind of circles or whatever associated with this phi. So it should be some analog of, I don't know, like an analog of QCD theta angle, or something which is and you are talking about, I'm not sure, because you are saying essentially about phi goes to infinity, right?
Yes.
So no, you see, that's why I try to commute it with notion of topology. It sounds, I mean.
Yeah, that's right. Yeah. So sort of on a technical level, the reason why we'll see this term contribute, or it might contribute, is that we will have 4-dimensional singularities. It actually turns out that if you just plug in Witten's bubble here, the Laplacian of Witten's bubble vanishes identically, so this term is not so important. But later it will play some role. And as to your question about topology, at least in flat space, these bubbles of nothing do carry some topological charge. It's called a bolt. When we talk about the de Sitter versions of these, they will actually be topologically indistinguishable from the vacuum. So, okay. So yes, it does have some connection. That's true. So if we just take this ansatz and we figure out what Witten's bubble reduces to, we get something like this. We get a log of the blackening function here, f, and so that's going to blow up near the horizon logarithmically. And we get a 4D metric, which is also very singular, blowing up near the bubble wall. So the whole thing looks quite singular from the point of view of this 4-dimensional reduction. But bear in mind that the 5D Ricci scalar vanishes. So things like the divergence in the 4D curvature and in the kinetic term for the modulus have to cancel against each other. All right, so to make this a CDL problem, we're almost there. CDL problems are just searching for O4 symmetric Euclidean solutions to 4D gravity plus a minimally coupled scalar. And the only difference, which is not particularly important, is that they work in a gauge where the full dependence in the full freedom in the 4-dimensional metric is just in this areal radius rho here. So this metric function rho is the full freedom in the 4-dimensional metrics. They've chosen their radial coordinate so that the coefficient is 1. And this is a radial coordinate, so it has to be larger than 0. And then the equations of motion that you get out of this, the CDL equations, are the field equation for the minimally coupled scalar and an Einstein equation for the metric function. And so the reduction of Witten's bubble in an appropriate coordinate transformation solves this system with u equals 0. So we'll talk a little bit about that. So here's just some plots to see how this looks. If we go into CDL form, we make a change of the radial coordinate. This is how it behaves near the bubble wall. It's just some power of xi here. And now we see again explicitly that phi is logarithmically diverging to infinity near xi equals 0, which is the bubble wall. And rho is going as a soft power of xi, so derivatives of rho are also blowing up.
But I'm sorry to interrupt, Patrick, but
sure.
You wrote equation for phi. If u equals 0, how dependence on psi enters in equation? It's linear equation, becomes linear equation, right? Where can you show equation again? Yeah. So there is no psi here, right? Anymore. If u equals 0, how phi? No.
So yeah, the equation that we have left is this one.
Right.
Right. So these pieces here. So there are solutions where it just there's two types of solutions. There's one where it just sits and stays at a value of psi, but there's another one which is singular where it comes to rest because friction stops it. So if we take in fact, I'll do a general solution of this equation for small xi and different values of the potential, and we'll see what the options are.
I see. So it comes not from this equation, but it comes from this equation for rho, right? Essentially.
Yeah, it has to solve both of them. So we have two functions.
No, but equation for phi becomes trivial, right? In a sense.
It has a trivial solution. Yeah, that's true.
No, not just constant, but also general solution is simple, right?
Well, the solution for rho that we're going to use is xi to the 1/3. So you pick up some xi dependence there.
I got it. Okay. No, because in this way, phi becomes kind of you can.
Yeah.
I mean, substitute.
Yeah, it becomes simple. Yeah. Right.
Okay. Thanks.
Right. Yeah. Very good. So so near the bubble wall, we get this log behavior. It's a little more complicated out here. Near the bubble wall, we get this power law behavior. And for Witten's bubble, we know that asymptotically it's flat, so rho has to go to just linear rho equals xi out here. So if you've done CDL problems before, this looks pretty weird. This looks very different from an ordinary CDL solution. And the difference can be entirely understood as differences in the boundary conditions. So normally what we do, we're given some potential and we want to find a CDL instanton. And we flip the potential upside down and we take a ball and we let it roll in the inverted potential. And the goal is to tune it so that it starts at exactly the right point so that asymptotically it ends at this local maximum corresponding to the inverted false vacuum. And because there's a friction term in quantum field theory, we can't just pick that point, we have to tune it to get the right answer. And the starting point corresponds to the initial condition. It corresponds to the center of the bubble. And we take for the velocity phi dot equals 0 or phi prime equals 0 at the starting point. So that's the ordinary problem. But for the bubble of nothing, instead what we find is that it solves a different CDL problem. It has 0 potential, so completely flat. And it starts from infinity with infinite negative velocity. So phi at c equals 0 is infinite. That's the center of the bubble. And it starts with a very high velocity coming in this way. And it turns out that in this case, it's the friction term rather than the potential that ultimately stops it. So this looks kind of strange.
I'm sorry again, but
Sure.
look, what was particular for the notion of false vacuum was that you still have kind of, this false vacuum, and you have, true vacuum, right? I mean, no, in the way you're approaching it now, you also should kind of say what is the original state and
What is the true vacuum? Yes.
Right. And again, maybe I'm missing this, but I do not see this particular point.
Right, precisely. And I would say that it's very unclear if there is a true vacuum that makes any sense. It's certainly not the case that there is some totally static, empty true vacuum of which the false vacuum is an excitation. The thing that this decays to, from the 5-dimensional perspective, is this expanding bubble, this hole in space, which is expanding out at the speed of light. So the true vacuum is a highly time-dependent thing that has this bubble expanding in it. And if you invert if you run time backwards to see where the Lorentzian bubble started, it fills most of the universe, and you have to collapse it in order to reach this.
Right, but in this way, it looks like then this nothing. It's nothing but how to say, run away, because we are living in run away, right? So then there is no kind of true vacuum, right? In a sense.
Agreed. Agreed. Yes, it's completely unclear if there is a sensible vacuum state of which ordinary flat Kaluza-Klein space is a metastable excitation. That is unclear.
Yeah, no, I mean, I recollecting, many years ago, Sasha Polyakov was the one who argued that this de Sitter vacuum is runaway.
Yes.
I mean, it was his idea. Even difficult for me to count number of years. But I remember this very well. He even talked about this in Aspen, at one point.
I guess there's in ordinary KK space, there's an even more immediate concern, which is that you get a perturbative potential generated by Casimir energies, and that causes immediate runaway, on timescales that are not exponentially small. We will deal with that momentarily by adding a potential to stabilize the modulus. But yeah, there's multiple types of runaway already in this theory, so it's really just a toy, I would say. Yeah.
Okay, thank you.
Thanks. So we saw divergences in the 4D perspective in the kinetic term and in the curvatures, but in 5 dimensions, this geometry is perfectly smooth. It's low curvature. The Ricci scalar vanishes. Other curvatures are of order 1 over the Kaluza-Klein scale. So if the Kaluza-Klein scale is somewhat large compared to UV cutoffs, everything looks under control. And what this tells us is that if for some reason we insist on working with this dimensionally reduced picture, which will in fact be useful, then the higher order terms in its action must organize themselves like 5D curvatures. So the divergences have to cancel amongst each other and leave over corrections that go like inverse powers of the Kaluza-Klein scale. So you might say, why bother doing this? The 5-dimensional thing clearly looks much better. Why torture yourself with these canceling divergences? And the reason is that there is one advantage, which is that it becomes easy to add a potential for our modulus phi and continue to solve the Cdl equations with singular initial conditions. So this gives us a way to talk about stabilizing the modulus and looking for bubble of nothing solutions. So these again are the potential terms in the Cdl equations, which are 0 for Witten's bubble. Okay, so this is just a repeat. Dimensional reduction plus the Coleman-DeLucia equations gives us a general method to study bubble of nothing decays if you have stabilized geometric moduli. And for reasons Arkady alluded to, in order for geometric moduli to be interesting at all, we have to assume that there was some kind of stabilization mechanism. So we want to ask which potentials make sense and admit bubble of nothing solutions. And secondly, what is the action if there is a corresponding Cdl decay this bubble of nothing is not particularly interesting unless its decay rate is faster than the ordinary CDL decay. So before I get going on that, I want to make a brief aside for anyone that follows the Swamplandy literature. You might be a little bit nervous at this point because we're talking about solutions where the size of an extra dimension pinches off. And there's something called the Swampland distance conjecture that says that a tower of states ought to become light. Well, it's a conjecture, but it's the conjecture is that some tower of states becomes light if you have a large traversal in a moduli space. For example, like a size of an extra dimension going to 0, you ought to get a tower of winding string modes that becomes light. Or if you take the radius to infinity, you ought to get a tower of KK modes. And so normally this is taken as some indication that you should not try and talk about different points in moduli space that are separated by too large of a distance at the same time. You shouldn't try and model those all in the same effective field theory, because it will become invalidated by this tower of states coming down. But this is a statement about the asymptotic homogeneous values of moduli, and it does not apply if what you have is just local excursions that are constrained to spatial distances which are relatively small, for example, of order the asymptotic Kaluza-Klein scale. And you can see this explicitly if you take something like a bubble of nothing core where a circle is pinching off, and you just try and quantize closed string states near this cap and ask, do winding string modes become light or do they do something else? And of course, once you draw this picture, you realize they must do something else. They should just slip off the cigar cap and propagate like free closed string states near the bubble wall. So the masses of closed string states don't become exponentially light near this bubble wall. They just become of order root string tension. A corollary to this is that we are going to be mainly interested in classical potentials. So when we talk about bubble solutions near the bubble wall here, the variation, spatial variations are large compared to, or they are order the Kaluza-Klein scale. So it doesn't really make sense to talk about effective potentials that apply when you have slowly varying moduli. You really need, if you want to do quantum corrections, you need the full effective action. So we'll mainly be interested just in classical contributions to the potential here.
Sorry, so I have a question about that. So
yes,
why do you care if you're in the swampland or not?
Oh, I don't for this talk, certainly. I just
because you're going to be describing some tunneling event of some phenomenon which doesn't necessarily need a quantum gravity description, does it?
That would be my attitude. I suppose that Swampland aficionados might, well, the reason I put that slide in is because I've gotten this question before from people that write Swampland papers. They say, well, look, you've got a radius pinching off somewhere. That means that you're going to infinity in field space, which is what we saw.
Yeah, no, I understand.
My description. Yeah, so is anything under control? And the answer is yes, it is under control. There's no tower of light states ruining anything. But yeah, I suppose the real Swampland question would be, does this analysis give us some new tool to allow us to identify points in the Swampland? And I'll make no conjecture about that here. Yeah, I'm just interested in these decays.
Okay.
But there is another way to about this problem, because in this way they believe that in certain sense the very notion of effective field theory does not work if with quantum gravity, right? I mean, no, it's another way to say the same as you are saying, but then kind of you cannot differentiate UV and infrared, right? And in this sense, when you are doing this, you are still making sense of effective field theory, right?
Right. So I'm using effective field theories here. I would phrase the Swampland stuff as saying not all effective field theories are equal, and some are just invalid. And I will not make any distinction here between whether the types of effective field theories that I'm using satisfy or don't satisfy Swampland criteria. I think probably they satisfy some, but since I'm going to talk about metastable de Sitter vacua, which has been a subject of a lot of Swampland writing lately, it could be that there's some body of literature that says that metastable de Sitter vacua don't make sense at all. And I'm going to assume that they do. So.
Okay. Okay. Yeah, I think in our situation it's better to be metastable.
Yes, yes. If I had to bet, I would say that. Yeah. So, so I'll be interested in potentials that do have a metastable vacuum somewhere, and since we're going to be interested in these bubble of nothing type tunneling things, basically what that means is that we need to, in some sense, maintain the possibility of interpreting phi as a 4 + n dimensional geometric pseudomodulus. So there must be some interpretation of this CDL solution as a non-singular higher dimensional gravitational instanton. So the types of classical potentials that we'll be interested in look roughly something like this. There's a decompactification limit over here, which sort of on general grounds can be argued needs to go to 0. And the compactification limit over here, which is the one we'll be interested in, can have various behaviors, at least at the classical level. And it will turn out that most of the bubble of nothing physics depends on what's going on out here. It depends on the asymptotics of the classical potential, and not so much what dynamics you assumed is responsible for the stabilization here. So to stabilize a modulus, you need some competition between various sources of stress energy, and it will turn out that in certain regimes largely factorizes from the question of whether or not a bubble of nothing solution exists. So I will mostly just model the minimum here and worry about the different possible asymptotics for what's happening out here in the compactification limit. Also, by virtue of the way that CDL problems work, we will never probe anything over here on the decompactification side. So it will be totally irrelevant what's going on over here for our purposes. Only the compactification side is going to matter. Okay, so we want to ask, for what potentials do bubble of nothing solutions still exist in this CDL framework? And a couple of necessary conditions both have to do with what's going on as phi blows up or near the bubble wall. First of all, we need to be able to solve the Cdl equations for small c. And second of all, we need to be able to uplift our solution to some 4 + n dimensional metric, which is smooth at c = 0. It doesn't have these singularities. So I won't be able to treat this in full generality, but as an example, let me look at potentials which are asymptotically exponential. So this gamma here is going to parameterize exponential potentials, and internal n spheres. So the internal manifold will compactify over, will be some n spheres. And I'll take an ansatz for the behavior of the fields phi and rho near the bubble wall, which looks like the Witten bubble, but with different exponents. So this alpha and this beta here we'll just leave free for now. So this is our ansatz that we'll look into. So first, let's check the 4 + n dimensional flatness and see what that requires. So if you want to do a general n manifold Einstein frame reduction, you start with your n + 4 dimensional Einstein Hilbert action here. These are the appropriate powers of or exponents of the modulus that you need to put in front of the 4-dimensional part, and the n-dimensional part you're reducing over, just some algebra to figure out what they are. And if you take this 4 + n dimensional parameterization of the metric and you stick it into this Einstein Hilbert action, then you find a metric or an action that looks like 4D Einstein gravity with our minimally coupled, canonically normalized scalar field phi. Again, this goofy Laplace term, and 2 sources of potential for the modulus. One is the higher dimensional cosmological constant, gives us an exponential potential. And notice it's a positive exponential at large phi. And any curvature on the n manifold that we reduce over also gives a positive exponential, although as far as the potential goes, the plus sign here means that this is a negative contribution to the phi potential. All right, so this is what the reduction of the action looks like. And just using this map, it allows us to check the 4-dimensional or the 4 + n dimensional flatness at the bubble wall. So we can take our ansatz for the behavior of the fields near the wall, stick it in, do some algebra. And what we find is that in order for the 4 + n dimensional geometry to be like R1 plus n times a finite sized S3, which means a bubble, that requires alpha to take a specific value. It has to be negative, and it has to be this root 2n over n plus 2. So all that we really constrained was this coefficient here.
But if you take a limit n equals to 0, which is 4 dimension, right? Then your alpha equals 0 and phi equals 0. Is it true?
Yes. I don't know that any of this makes sense with n equals 0.
Why not? It does, because look at your metric, it just becomes 4-dimensional metric and n equals 0.
Yes, I think that's fine. Okay, this line doesn't make sense, I would say here. Yeah, that line doesn't make sense. But yes, that's true. There is a trivial limit where we don't compactify on anything, and then we just get back a 4-dimensional metric. That's right. Kaluza-Klein theory would be for an S1 and n equals 1.
Mm-hmm.
Yeah,
and it would be phi effectively it would disappear, right? Essentially.
Yes, phi would go away. That's right.
Mm-hmm.
Good. So okay, so that tells us one constraint from flatness. The other thing we have to do is solve the Cdl equations. So we can take our ansatz at least near the bubble wall and stick them into the Cdl equations, and again turn the crank and see what kinds of constraints we get. So again, I won't show the algebra, but in the small xc limit, you find two cases that admit solutions. One is alpha times gamma. Again, alpha is this sort of exponent of xc in the phi behavior, and gamma tells you how the potential behaves. Alpha times gamma greater than -2, and alpha times gamma equals -2. And for all values alpha times gamma less than -2, there's no solution. So if the product is greater than -2, then you find that you have to have n equals 1, and you get specific predictions for alpha and beta in that case. In the case alpha times gamma is -2, n can be other things, and you get a prediction for beta. But because we have now a constraint on alpha and a constraint on alpha times gamma, we'll also be able to compute gamma. So let's look at each one of these cases and see a little more intuitively what they mean. At this point, they're just some numbers. So if alpha times gamma is greater than -2, well, first of all, we found that n equals 1. That tells us that we're working with an S1. Alpha is minus root 2/3. That's exactly the behavior of the Witten bubble. And beta equals 1/3. The power of xc in rho also is exactly like the Witten bubble. So what we find is that we should have exactly Witten-like behavior near the bubble wall as long as the potential grows as slowly as e to the root 6 phi. And this is quite funny because Witten's bubble has a potential which is asymptotically 0. Here we're saying that you can still find a solution with a smooth bubble wall as long as the potential doesn't grow faster than a certain exponential. So this is a little surprise to me. And this constraint on this root 6 here comes from alpha times gamma greater than -2. Alpha was negative, so you stick this in and divide through, and you find that gamma has to be smaller than root 6. So what does that mean? What sorts of potential terms can give you an exponential which grows more slowly than root 6? And perhaps the simplest example is the cosmological constant. So the higher dimensional CC lambda gives you a potential here. If you stick in n equals 1, it goes like e to the root 2/3 phi. So we find that for cases where the potential goes to 0, indeed, we'll get some Witten-like behavior, but also cases where the asymptotic modulus potential is governed by the 5-dimensional CC falls into this class. So we'll look at some numerical solutions that actually do solve this later. The other case was alpha times gamma equals -2. And here, because alpha is this negative number constrained by flatness, we can compute gamma. So we also constrain beta and r, but the more interesting thing is that we get a fixed value of gamma, and gamma is our exponent in the potential that matches exactly what you would get from n-dimensional curvature. So we find...
But you will have r equals 0, right, for n equal 1?
Yes, so for this, this case, it makes more sense, well, yes and no. The c here for n equals 1 goes like n minus 1, so if I plug that in, that will cancel out. And this minus sign cancels the relative sign. So actually there is there is an interpretation for n equals 1, which is that axion flux on an S1 does the same thing. But in terms of the curvature interpretation of an Sn, there's no curvature for S1, so we need n greater than or equal to 2 for that case. Yeah, right, exactly. So so for Sn, yeah, we have to think about n greater than or equal to 2, and we get some ordinary curvature of the n sphere here. So what we learn is that if the asymptotic potential for this pseudomodulus is governed by the curvature of the internal manifold that we're compactifying on, then that corresponds to this type of case, and we'll get different exponents. So for Witten's bubble, rho grew like c to the 1/3 near the bubble wall. Here, if say we compactify on a 2-sphere, we find beta is a half. So we get these different types of exponents for the growth. There are other sources of 4 plus n-dimensional stress energy. Perhaps the first one that you may think of is wrapping some n-form flux on the internal manifold. That turns out to give a potential which grows faster than curvature for all n greater than 1. If n equals 1, it's this case I just mentioned where you put axion flux and it behaves like a curvature, even though there's no curvature for S1. But if I stick to ordinary gauge field fluxes, this is going to be too singular to admit a bubble of nothing solution. You'll only be able to construct a bubble of nothing if you also add some dynamical charges that can screen this flux. And actually, there are some nice papers that study explicit realizations of this in 60 Einstein-Maxwell flux compactifications from about a decade ago. But this is these can be generalized and sort of understood in this framework. Other generalizations, we could add multiple fluxes, wrapping on different internal manifolds, p-branes, and so on. I won't do any of that today, but the framework can sort of address that. Okay, so let me just recap what we learned from this in sort of the simplest terms possible. One is that if there's an asymptotic potential that behaves like it goes to 0, in other words, there's no flux on the internal manifold, no higher dimensional CC, no curvature, then we should have some Witten-like behavior near the bubble wall. There is an asymptotic behavior where you're dominated by the higher dimensional CC, and we again learned that this thing should have bubble of nothing solutions that behave similar to Euclidean Schwarzschild. And the third case, which is particularly simple, is if you're curvature dominated. If there is flux, we do need to screen, and you can try and determine that dynamically, but for now, I'll just ignore fluxes.
I'm sorry but I'd like to understand it at this point. You're implying that all those cases, it is still kind of decay or run away, or or there is, it's not a stability, right? In any case, or what?
This, yeah, so these will represent non-perturbative instabilities, and whether or not the classical potential admits a perturbative instability depends on.
Yeah, right. But there is no solution with kind of going to like a false vacuum or whatever. I mean, decay to some stable vacuum. It doesn't show up in this way, right?
That is correct. Yep. Yep. Looks very different.
Uh-huh.
So if I draw a potential like this, which also illustrates Arkady's point. So this is a case where I've added by hand some stabilizing dynamics far from the compactification limit. And in the compactification limit, I'm allowing phi to go to 0. Both the CDL tunneling and the bubble of nothing tunneling will be run away. But they tunnel to different points. So the CDL tunneling is to some finite point over here, and the bubble of nothing is a decay to the compactification limit in this picture, which is why the title of the talk is Decays to Infinity. So I will assume that, that we have a complicated set of dynamics that gives you a de Sitter minimum at some largish value of the geometric modulus size. So R is bigger than string scale. And in the simplest case, we can try and study what happens if the potential goes to 0 asymptotically.
So, so I have a question here. So
yes,
in your model for the potential, your higher dimensional model, the CC there could have been positive or negative. Is that right?
True. Yes, that is true. And that
And
will
so-
change the sign of the potential. Yeah.
And so, but you're going to consider what sign of the higher dimensional CC then?
I'll show a couple of slides towards the end where it's positive. And I don't think I have numerical results for the curvature case, which is negative definite. But here it's 0. In this picture, that higher dimensional CC has to vanish.
Oh, so you take it to be 0.
Yeah.
So do you consider any ADS cases in higher dimension, like ADS 5?
That's a good question. I have not done any analysis of that yet, but it should exist. In fact, it turns out that the higher dimensional CC does almost nothing to the bubble of nothing solutions. It's like a perturbation on Witten's bubble for most cases. So and that's, I think, regardless of the sign.
Okay, thanks.
Yeah, good question. Yeah.
Can I ask a bad question, actually?
Very much so.
Might have addressed it already, but in the higher dimensional theory, there might just be a potential for the scalar already, maybe some polynomial potential, but you probably don't have to worry about it for what you're doing, because when you compactify in the dimensionally reduced theory, there's always this exponential term from quantification. Is that right?
Yeah, so
that dominates over whatever else you would have added in 5D in the regime of interest, and so you don't have to even talk about that. Is that right?
Well, yeah, that's a good question. I'd have to think about it a little bit. So phi in the higher dimensional theory, phi is just some component of the metric. So any potential term that I write down has to come from covariant expressions in terms of the full metric, and so then it's a question. Yeah. If you had some logs that appeared from integrating some stuff out, then I think you could get polynomial terms. As I said, kind of for our purposes, since we're going to be worried about what's going on in a regime of solutions where there's rapid variation of phi spatially, it's hard to say what quantum corrections do near the bubble wall. Asymptotically, quantum corrections might be important for stabilizing your potential, but what they do to sort of bubble structure near the wall is completely unclear, and you cannot model it with an effective potential.
Okay, but actually, maybe I should have asked a different question then to make any sense. So, what would happen if instead of just having just Einstein gravity in the higher dimensional theory, you also had some matter? Then you would inherit some matter in the 4D theory, and everything would get somewhat more complicated. But do you know if it should affect things qualitatively?
I think, for example, that if you allow, say, some, so it depends on the state of the matter, of course, and if it's in vacuum, then it will add some quantum corrections, which again are not something that that we can really handle without computing the full effective action. Assuming that it's perturbative, that will be small. If the state of the matter is non-trivial, like you have some flux wrapped around the dimension, or you put a p-brane around it, then it does contribute to the classical potential. So the flux cases are ones that require some complication to describe. You need an extra degree of freedom that controls sort of the Schwinger radius where you nucleate and screen that flux. Otherwise, you don't have.
What if you put a fermion? Then you have to specify boundary conditions around that.
Yes, for right. Right. So so for the 5D case, these may not exist if there's an inappropriate spin structure. I have to admit that I find this very confusing because we're starting from a metastable de Sitter state, which breaks supersymmetry anyway. But the spin argument may be stronger than that in the S1 case. But if you consider, say, an S2, then pi1 is 0, and you don't have that argument anymore. Right, so. So some cases might be shut off by that, and other cases maybe not. I think it's it's an interesting question. So for any 5D case, I'll assume a Shirk-Schwarz type compactification.
Excellent. I see.
Yeah, good question. Okay, so so let's look at the simplest case where we have a potential that, from the CDL perspective, falls to 0 asymptotically. And we learned from our previous analysis, at least within our ansatz, we will need n equals 1, which is ordinary KK theory, And the small c initial conditions for the bubble of nothing are Witten-like. So just to remind you, what that means is that instead of a CDL initial condition where we start at rest and we try and roll to this false vacuum maximum, we'll have a bubble of nothing initial condition where we shoot in a singular way from infinity at high velocity, and friction will be what saves us. So the question is, once we've added some potentials, what does the bubble of nothing look like, and which rate is faster? So one point to make is that despite its small radius Witten-like behavior, the bubble of nothing actually has to differ from Witten's bubble at large radius, because we've assumed a de Sitter vacuum, and Euclidean de Sitter is compact, so the bubble of nothing has to be asymptotically compact, whereas Witten's bubble is asymptotically flat and non-compact. And the way to see this at the level of the Cdl equations, this is the derivative of the rho equation, the derivative of the Einstein equation. At large radius, far from the bubble, the modulus stops moving. It approaches the false vacuum. And so rho double prime, if u is 0, it just goes, rho goes to a constant, or rho goes linearly, rho goes to c, which is the asymptotically flat case. But if u is positive at large radius, corresponding to a metastable de Sitter vacuum, then rho double prime changes sign. So rho double prime changes sign and eventually drives rho to 0. Your manifold ends, and there's a requirement of smoothness at that point, which tells you that phi prime has to be 0 when rho equals 0. So that's sort of, in one sense, you might expect that, say, for small potentials and small vacuum energies, you should basically have a Witten bubble, but at least at the level of the field profiles, they have to be very different far from the bubble core. And I'll come back to that in a minute and discuss that a little more. So the general strategy then, just to recap, is that we're going to take the Cdl equations, we're going to stick in a modulus potential that hopefully makes some sense as a higher dimensional picture. And then for that given potential, we are going to use the correct small c initial conditions in order to do shooting, numerically or analytically or whatever. And this then makes the problem exactly like ordinary CDL, except for the singular initial conditions, which have been carefully chosen so that they're not singular in the presumed 4+ n dimensional theory. So our previous analysis indeed tells us that we'll have some smooth, non-singular higher dimensional interpretation if this shooting solution exists. So before I get on to numerics, I want to discuss this little puzzle that I just raised and try and build a very simple analytic model. How do I embed Witten's bubble into a de Sitter space with some large Hubble scale? So if our Hubble scale is large compared to the compactification scale, you would expect physically that there should be a bubble of nothing that looks approximately like Witten's bubble at short distances. And so how do we see that this embedding makes sense? Also, how do we see that we get the Witten action out? It can't come from GHY terms because the full 5D manifold is now compact. So we have to do something else to get the action out. So here's about the stupidest model that you can imagine putting together. Just make a kind of Franken model where you take Witten's bubble and you weld it at some point, C star, some spatial point, C star, to the Euclidean vacuum. And let me just assume that we're working with ds4 across S1 for our Euclidean vacuum, and that the minimum of the potential is at phi equals 0. We can take that without loss of generality. So here's the Witten behavior again, the singular logarithmically exploding thing near the bubble core, and here is the false vacuum behavior. And to put the CDL metric into, or to put de Sitter space into CDL form, it turns out that ds4 corresponds to rho goes like sine of c. So this is the sine function corresponding to the false vacuum, and this is the Witten behavior of rho. So we're going to try and glue here at some welding point C star and see if that makes any sense. So, this does make some sense intuitively if you get through that barrier region quickly, if the potential doesn't really play much role in setting the profiles apart from where you stop. But we need to make sure that we can recover the Witten action since the assumption is that this potential is only a small perturbation. And the puzzle here is that we don't have any GHY terms since our 5D manifold is compact and smooth. So we've got, let's see if I can go back. We've got a smooth bubble cap here at small c, and over here where rho goes to 0, phi prime is 0. This is also a smooth point. So we just have various spheres capping off at these two ends, and we just have a compact manifold. I actually shouldn't write smooth here in the Franken model for reasons we'll see in a second, but at least it's compact. So we know that on the Witten bubble side, so in this region, the 5D Ricci scalar for Witten vanishes and the CC vanishes, which tells us that the bulk Einstein-Hilbert action is just 0 inside C star. And the exterior is ds4 cross s1. We can compute that that's the full action of ds4 plus some corrections that are sensitive to the bubble size. The rho star here is rho evaluated at the junction point. So these are two contributions, but they're not the only ones. Because we've done a sort of cold weld at the junction, we need to make sure that we include any contributions from discontinuities and derivatives. So we'll assume that we have continuity in this model, but approximate the derivatives by the Witten bubble or the false vacuum. Okay, and this is again some algebraic suffering, but there turns out there are two derivative terms that give junction terms. One of them is our friend the Laplacian term, and the other comes from second derivatives of the metric. And these behave exactly like GHY terms at the junction. So it turns out that you plug and chug and you evaluate what this gives you. You get exactly Witten's action back from the Laplacian term, and you get some other thing that depends on the vacuum energy and on the location of the junction from this guy. So this is not terribly intuitive at this point. We just have a bunch of different pieces. We have to add them all up and subtract the false vacuum in order to get the tunneling exponent. And approximately for small vacuum energy, you get some ugly expression like this. But if you plot it as a function of where the join point is, or like the size of the bubble, you find it has a nice property. It has typically a local maximum. And a local maximum is good because it tells us, first of all, that it suggests the existence of a stationary point. And second of all, that it's a saddle point. There's a direction here with a negative second derivative. So that's good for an interpretation as a tunneling process. And I've grayed out a region over here where this model isn't good because this assumption of continuity starts breaking down. But at least in this region here, we have a reasonable approximation. All the inputs are self-consistent. And what we find is that for various values of the vacuum energy, typically the maximum here is close to pi squared r squared mp squared. So this is the action normalized to r squared mp squared, pi squared is 10. And so most of these predict an action which is very close to Witten's bubble up to small corrections. So this is good. This tells us that it does make some sense to consider these bubbles in asymptotically de Sitter spaces. It has nice properties. It has this local maximum, which points to the existence of a negative mode. And the particularly relevant thing about bubbles of nothing is that the rate is non-zero in the limit that the vacuum energy goes to 0. So normally CDL has a rate which in sort of the flat space limit is the exponent has an epsilon to the -4 in it. Once you include gravity, the exponent has an epsilon to the -1 in it. So they diverge and the rate goes to 0 as epsilon goes to 0. But for bubbles of nothing, the epsilon drops out and we just have this pi squared r squared mp squared, which just depends on some presumption about the higher dimensional kk scale. And then there are corrections to this that you can compute perturbatively, or you don't exactly end up at pi squared r squared. So let me see. All right, so I'm running, looks like I'm running a little late. So maybe I'll start thinking about wrapping up. We had a few questions, but I will maybe skip some stuff towards the end here. Okay, so right. So we would expect that that as the potential barrier that we put in becomes more important, the model ought to break down, and we can make kind of a dimensional grounds estimate for this. And it comes out that so when the Witten action r squared mp squared is comparable to the contribution to the action from the potential, u naught here is like the barrier height, then we would expect that these approximations are starting to break down. Another thing that can break down is that if we were actually going to do shooting, we need a shooting variable. And the relevant thing to use is that the small xc Witten bubble could be characterized by some radius r, which is different from the asymptotic circle size when you have the potential. So you can think of r as the shooting variable. And in the previous analysis, I just assumed that r equals r5 and that this was small. So to study more general potentials, we have to resort to numerics. But we can check then what this, how well they match just the naive Witten bubble guess numerically. So here's a whole bunch of example potentials. I've normalized the barrier height to 1 here, and they all fall off to 0 as we assumed for the simplest case. We have different vacuum energies, we have different widths of the potential, and you can run these all through a shooting code and see what you get. So here is some results. This is a subset of results where we just fixed the width of the barrier and we varied the vacuum energy. And the interesting thing here, a little bit of a surprise, is that we find 2 branches of solutions. So the axes here are like the shooting variable versus the asymptotic KK scale R5. And we find that R does equal R5 for small KK scale on 1 branch of solutions. But that breaks down when so when this becomes of order 1, the potential is becoming important, and we see that R equals R5 breaks down. There's also this whole other branch of solutions here where R is not R5, and what does that mean? So if you look at the profiles that we get out and you look at the actions, you find that these branches correspond to something very bubble of nothing-like, very Witten-like, and something which is very CDL-like. And so the physical picture of this, what's going on, is that on the bubble of nothing branch, you have a high velocity, you shoot in, you mostly ignore the potential, and you come to rest because of friction at the point you wanted. But there's a whole other branch where you shoot in with the bubble of nothing initial conditions, but you stop too soon. Friction stops you here, and then you have to roll the rest of the way. It's basically like gluing a bubble of nothing to the interior of a Cdl instanton. So roughly on these branches, there's the Cdl branch where the initial conditions aren't important. You stop and you roll. And then there's a bubble of nothing branch where the potential is not important. And you just blow through it and reach the origin. So here are some profiles. Here is a plot of the action. Let me actually just go to this, this plot. This shows for a particular potential what the action does on these 2 branches. So this is the bubble of nothing branch here. As we scan over a bunch of different values of the KK radius, it behaves like pi squared r squared to a good approximation, all the way to the point where it intersects with the Cdl branch, which doesn't care at all about the size of the extra dimension. So this is basically the Cdl action we would have computed with ordinary Cdl initial conditions. And when they intersect, you actually find no bubble of nothing solution for any larger value of the KK scale. So there is some maximum value of R for any potential, which you can roughly estimate by the time when the Cdl action becomes less than the bubble of nothing action. And for any value of the KK scale where you do find a bubble of nothing solution, its action is always a lot lower than the CDL rate. So this is some indication that these bubbles of nothing are much more important than the CDL instanton when they exist. All right, I am going to very briefly just show that you can do the same thing with the cosmological constant. So the 5D cosmological constant that Tony was asking about. Here I did choose it to be positive, so so a higher dimensional de Sitter case. And this is interesting because let me go back and show the upright potential. if this is our metastable vacuum, it doesn't look metastable at all from the point of view of ordinary CDL tunneling, but a bubble of nothing solution still exists, because when you turn it upside down, you can imagine shooting in up this hill. So there is no CDL-like initial condition where you roll to the false vacuum, but there is a bubble of nothing type 1 where you shoot in and you stop at the maximum. And so you can do numerics on this and find, again, Witten's bubble is a pretty good model. Pi squared R squared is still a pretty good estimate up to order 1 numbers for the action. And yeah, this was quite a surprise because the potential doesn't look unstable at all. Similar stuff in the curvature case. I'll skip through this, but it follows kind of the same picture. And you can glue a different type of solution to the interior. All right, so I've run over time, so let me just summarize and conclude. So we looked at bubble of nothing type tunneling and tried to define what it means in general, where you have a landscape with a potential for some geometric moduli. So how do you sort of formally address this problem in the general case, or as general a case as possible, and compare its action to other decay modes? This only makes sense if you have some stabilized moduli, at least perturbatively. But in that case, you can formulate it as this CDL problem, which is ugly from the point of view of singularities, but convenient for trying to find solutions numerically. And we find that the existence of these bubbles of nothing really depend only on the asymptotics of the potential, which gives you some factorization or some insensitivity to the precise dynamics that stabilized the vacuum. We get parametrically faster than CDL decays in all the cases that we looked at. And this is mainly because there is no 1/energy gap in the Euclidean action for bubbles of nothing. It depends only on the size of the extra dimension. All right, so thanks for listening, and I'll stop there.
All right, thanks a lot, Patrick. We can give you some virtual applause. Here you go.
Thank you.
If there are any questions.
So what did you say you expected for ADS in higher dimensions then?
I expect that there will still be these solutions that exist. So in that case, once you flip the potential over, it's actually helping you come in. So right. It's inverted potential is going up. So I would expect that's good, and it's easier to find solutions. You can come in even more slowly. But I haven't investigated yet. So that is a good question.
But what? Yeah, because why did you look at the Sitter first then? Is it because there's this qualitatively different solution? Is that why you wanted to look at that?
Why did I do that first? I think it was because, so yeah, the reason is because I knew some 5-dimensional solutions and 6-dimensional solutions that I thought could replace the Witten bubble for making this Franken model for gluing together. And those probably exist in the ADS case, but I just didn't know what they were. Yeah, yeah. So for example, in the curvature dominated case, it turns out you can do this nice reduction, an anisotropic slicing of 6-dimensional de Sitter, and treat that as your bubble interior. And you get a nice effective potential thing again with a local maximum. This is also still work in progress. So I'll definitely look at that.
I see. Yeah. So it was more of a practical thing. That's why you did that first.
Yeah. Yeah. But ADS is a good case, and bubbles of nothing are known to exist in ADS.
Exactly. Yeah. That's why I was asking.
Yeah.
I have a question maybe related to this, and a second one about the DS case. So for ADS, if I have some ADS space, there's always a CFT interpretation for that through gauge gravity duality. And compactifying a CFT on a circle should be a well-defined thing to do and shouldn't lead to any instability. So naively, there should be some major difference between ADS and DS because of this kind of perspective.
Yeah.
I really imagine DS is very subtle, and bad things happen if you compactify higher dimensional DS spaces. But if you have a random 5D ADS space, the dual is some CFT. So it seems hard to believe it's unstable.
Yeah, but it'll probably have an instanton interpretation in the CFT, probably.
I'm not sure because like physically here you're decaying to some completely different space-time geometry, right? There's a bubble of nothing that just expands, and then what do you have left? But in ADS, if that happened, what would you say about the dual field theory, right? This would be some really weird time-dependent process in the CFT,
right?
That appeared because you chose to compactify it in a circle. So like maybe, but that sounds like a story that could be elaborated on.
There is a literature on this, and I'm ashamed to say I don't know what the resolution was. There was a point in time. I think there was a point in time where this was taken as a real puzzle. That what could this possibly mean in the CFT? And I don't know what the resolution was of that. That's a good question. If you make these bubbles large enough in ADS, then they have different properties related to the fact that specific heats of large black holes change sign in ADS. Similarly, there are static solutions that are large bubbles that are stable in ADS. So I also don't know what the small bubbles behave like they're just flat space Witten bubbles, but that may be related.
I wonder, maybe it's irrelevant, but still, maybe you have an opinion on this, because I recently looked at this. It was a paper by Rabinovich, then this Slava from Munich, and so three authors. Anyway, they claim that there's an important quantum correction. In the case that where CDL procedure does not work, standard, that they claim that there are new type of solution instead of CDL. So in situation where CDL does not produce solution, they claim another one. And maybe it's irrelevant to what you are talking about, but because it's not about this bubble of nothing. But I wonder if you have any. Did you notice this? And if you do, what do you think?
Well, first of all, unfortunately, I don't know that paper. Were you saying that it doesn't exist at like the semi-classical level, but once you add an effective potential to it, then it exists? Was that the?
Yeah. So in this way, they're claiming that. Yeah, you would say that it does not exist. Solution doesn't exist, but then they're claiming that there are quantum corrections which effectively changing potential in new type of solution would show up. It is a claim. Okay. I'm sorry.
There's some debate about that, I guess. That's how people argue that the standard model is unstable. You need large quantum corrections in order to see that there's an instability at large field values of the Higgs. Without them, it looks totally stable. And how do you add those systematically into a treatment of the semi-classical expansion? And as far as I know, the attitude is that, well, you can sort of get away with RG corrections. You can sort of get away with including logs in the effective potential, but anything else is not parametrically larger than other quantum corrections that you're omitting. So that's related to this business of large curvatures near not large curvatures, but large variations in the fields near the bubble wall. So
that's why I actually ask you. But so in this way, you do not think that there is any kind of a real status of this, that it could that it is just very much hypothetical in this sense, or?
I think it's hard to make it systematic apart from what is the standard CDL prescription, where you would compute the quantum corrections from fluctuations around a semi-classical solution. It's not you can't do that if there's no classical instability.
Right. Yeah, no, it's okay. It's my attitude too. That how you would call it correction if there is no leading approximation.
Big correction. Yeah. So you have to find a way to make it sort of systematic. And Matt Schwartz has some nice papers trying to delineate when you can consider this legitimate to include those quantum corrections in the potential that you use to find the semi-classical solution in the first place, and when that's not legitimate. But I haven't totally absorbed My rough impression was you could kind of get away if it was just big logs, but anything else you really couldn't.
Okay, thank you.
Thanks, Arkady.
So I just have one more question, if it's okay.
Of course.
If you add an R squared term, you know that you turn on another scalar mode, but that would be in addition to what you called the var phi, right?
Right. Yeah, that's a good point. Yeah, I haven't looked into that, but then that will presumably mix and have its own. So this was all toy model single modulus and geometric modulus moreover.
Yeah. Because that's typically what happens in 4D when you do add R square terms, then you get scalar potentials coming out automatically. Yeah. Okay.
Right. That's a good point. Yeah. I have a lot of work to do.
Right.
Yeah, this is just a first pass simplest case, but
sure. Yeah.
Yeah, good point.
I also wonder that I do not see that your collaborators are participating in this discussion. So you are so much dominating.
No, I should have sent them the link. I don't know. My attitude, I actually thought a little bit about sending links to people, but personally, as I said at the beginning, I think about deleting Zoom every day. So if they don't have to be here, then let them enjoy. Isabel is in California. Well, you're in California. You're right next to Isabel.
Yeah, but I used to see her in the institute, but not anymore.
Yeah, you should both be on the beach. It's just enjoy life while you can. It's
well, we can only dream of that here. So
yeah, it's going to be a while. It's going to be a long, cold winter.
Any other question?
I have a question. Is it possible to have bubbles of nothing when you don't have geometric moduli? When you have some moduli, but they don't have a geometric interpretation?
Yeah, certainly, you could even phrase that more sort of from this four-dimensional perspective. These solutions exist. This is a theory. I can write them down, and it turns out that the action is finite. Okay, all of the curvatures and things are blowing up, but should I take this seriously? And I think what you really need is an argument that that corrections are organized in a way that prevents you from just spoiling the whole thing by adding some higher dimension operators. So you need that those should not just suddenly be infinite as soon as you turn them on. I know how to do that with these geometric moduli. That makes sense. I know what the compactification limit means, and I know how to study smoothness there. For other moduli, less clear. Maybe if they had a dual that was a geometric modulus. Yeah, I don't know. It's a good question. I'm also not enough of a string theorist, I'm afraid, to. Yeah. Good.
Okay, I'll stop the recording if there are